Hi, welcome to Intermolecular Forces, Solids and Liquids. My name is Dr. English. Today we're going to be talking about the difference between intramolecular forces and intermolecular forces. Specifically, we're going to look at what's the difference between these two types of forces: ion-dipole forces, dipole-dipole forces, London dispersion forces, hydrogen bonding, and finally, the impact of intermolecular forces on concepts like boiling point and melting point. Intra and intermolecular forces. Intramolecular forces are forces that exist within a compound. These include ionic, covalent, and metallic bonds. So ionic, it's that Coulombic attraction between the positive ions and the negative ions. For covalent, it's the sharing of valence electrons, as we see in these double bonds. And for metallic bonds, it's the sharing of electrons in that sea of electrons between positively charged nuclei. Intermolecular forces are forces that exist between molecules. Between molecules. That's very, very important. These are also known as van der Waals forces. And there's three different types of intermolecular forces. There's ion-dipole forces, dipole-dipole forces with a specific type of dipole-dipole force called hydrogen bonding, and London dispersion forces. What is the purpose of knowing anything about intermolecular forces? Well, any type of matter contains some type of intermolecular force. Whether it is a solid, a liquid, or a gas, they all contain intermolecular forces. Intermolecular forces are involved in phase change. So while I might have a representative of a neutral compound down here as a liquid, if I add some heat, it will go into a gas, and we will break intermolecular forces, but not intramolecular forces. Now let's talk about ion-dipole forces. These occur between neutral molecules and ions. So again, neutral molecules and ions. So here I have a representation of sodium chloride with positive ions and negative ions. Then I have water molecules coming in to attack that sodium chloride compound, and each water molecule will surround a negatively charged chloride ion so that the positive part of the water molecules, the hydrogens, which are slightly positive, are facing inward. Meanwhile, the sodium ion, represented as these purple spheres right here, is a positively charged ion. Therefore, the oxygen, which has a slightly negative charge, will be facing inward. And what happens here is the water molecules will arrange themselves so the positive ends are towards the chlorine ions and the negative ends are towards the sodium ions. And that is known as an ion-dipole force of attraction, because what we have here are weak intermolecular forces between the water molecules and the ions, like we see right here and right here. So they're very weak intermolecular forces of attraction. Dipole-dipole forces. Dipole-dipole forces occur between molecules that have permanent dipoles, where one end will be slightly positive and one end will be slightly negative. Such molecules contain polar covalent bonds and a geometry that forms polar molecules. This results in a permanent dipole. Recall, polar bonds occur when electrons are not shared equally in the bond due to differences in electronegativity between the atoms in the covalent bond. So here's an example. We have sulfur with its 6 valence electrons, and then hydrogen, each with its 1 valence electrons, and we form covalent bonds here. Here they are, sharing their valence electrons. So the sulfur will have a slightly negative charge, while the hydrogens will have a slightly positive charge. This is known as a permanent dipole. The hydrogens will always be slightly positive, the sulfur will always be slightly negative. A structural representation of this can be seen here. Sulfur is slightly negative and the hydrogens are slightly positive. Dipole forces hydrogen chloride. In this compound, a permanent dipole occurs due to the difference in electronegativity between the hydrogen and the chlorine atoms. As a result, dipole forces exist between the molecules. So here we have some hydrogen chloride molecules. Again, the hydrogen is going to be slightly positive, the chloride is going to be slightly negative. We can add in representations of weak intermolecular forces, these dipole forces, that is holding this hydrogen chloride together. So each of the slightly positive is attracted to an end of the hydrogen chloride molecule that is slightly negative. Dipole-dipole forces are generally weaker than ion-dipole forces. They are effective only when polar molecules are very close together. Dipole attractions become weaker as the distance between the individual molecules increase. Dipole attractions are stronger attractions than London dispersion forces, and therefore dipole molecules have higher normal boiling points than nonpolar molecules of comparable size. For molecules of approximately equal mass and size, the strength of the intermolecular attractions increase with increasing polarity. London dispersion forces. These forces occur between nonpolar molecules. Technically, all molecules contain dispersion forces since intermolecular forces are additive, meaning all nonpolar molecules will have dispersion forces, and polar molecules will have dispersion forces and dipole-dipole forces, so they are additive. Molecules must be very close together for such forces to exist. We need high pressure and low temperature for this to happen. These are the weakest of all the intermolecular attractions, and as a result, nonpolar molecular substances have the lowest normal boiling points of all liquids. A representation of dispersion forces. Let's look at diatomic nitrogen. Now this is a nonpolar molecule, and we have shared pairs of electrons between these two nitrogens. But at any one point in time, one nitrogen might become slightly positive and the other nitrogen might become slightly negative as the electrons move back and forth between these two atoms. As a result, we can have diatomic nitrogen molecules getting close together and doing something known as inducing a dipole, making a dipole happen just based on proximity. When this happens, we have these very weak intermolecular forces of attraction that occur between the diatomic nitrogen of one molecule and the diatomic nitrogen of another molecule. But remember, you need extremely low temperatures and high pressures for this to exist. Another representation of dispersion forces, carbon dioxide. Here's carbon dioxide. Again, we have a nonpolar molecule where the electrons are shared equally between these two oxygens. Of course, the electrons are moving back and forth as they move through. Carbon dioxide can be a resonance structure, so at any one time, this end might be slightly positive and this end might be slightly negative as the electrons move around. As a result, we can have carbon dioxide represented as so, where we might say this is in a liquid CO2 situation, and then we can have forces of attraction that occur between neighboring carbon dioxide molecules. Or we could compress them more and lower the temperature and line them up in a row where they're uniformly positioned. And then we can add in our intermolecular forces of attractions, our dispersion forces, and have something like dry ice. So this could be a model for dispersion forces in carbon dioxide in dry ice. Hydrogen bonding occurs between hydrogen and highly electronegative elements. Particularly strong dipole forces occur between molecules in which hydrogen is bound to a highly electronegative atom, such as oxygen, fluorine, and nitrogen. Considered a unique dipole-dipole attraction, so hydrogen bonding actually falls under dipole-dipole forces. Because fluorine, nitrogen, and oxygen are so electronegative, a bond between hydrogen and any one of these elements is quite polar. Liquids whose molecules are held together by hydrogen bonding, like water, have unusually high normal boiling points. We can see that in this particular graph, where we have oxygen, fluorine, and nitrogen all coming out of period 2, and compared to the rest of the molecules that we see here, they all have high boiling points. Elements in period 3, 4, and 5 have much lower boiling points because those particular elements that are involved do not have a great enough electronegativity difference between the hydrogen and themselves. A representation of hydrogen bonding with fluorine. Molecules of hydrogen fluoride connected by hydrogen bonds. So here's my hydrogen fluoride, where the hydrogen is slightly positive and the fluorine is slightly negative. And we can see the hydrogen bonding that would occur, this force of attraction, between neighboring hydrogen fluoride molecules. A representation of hydrogen bonding with oxygen. In certain conditions, water molecules will orient to optimize attractions between the positive and negative poles of the molecules. So here we have some water molecules, and they have oriented themselves so they can make those connections, those force of attractions by hydrogen bonding between themselves and form things like liquid water and ice. When we add heat to a situation like this, we break the hydrogen bonding, we break the intermolecular forces, and we create water vapor. But at no point in time was any covalent bond harmed during this process. Here's the last representation of hydrogen bonding, and it is with nitrogen. Molecules of ammonia are connected by hydrogen bonds. So here's our molecules of ammonia. They are arranged so they can form those weak intermolecular forces of attraction via hydrogen bonding between neighboring molecules and have liquid ammonia, where the hydrogen is slightly positive on one end and the nitrogen is slightly negative on the other end of the force of attraction. Impact of intermolecular forces. Intermolecular forces, also known as van der Waals forces, have direct impact on boiling point, where the stronger the attractive forces, the higher the boiling point, and melting point. The stronger the attractive forces, the higher the melting point. Large molecules tend to have a greater ability to polarize due to the greater number of electrons and the fact that electrons are farther from the nucleus. As a result, the strength of dispersion forces increases as a molecular size increases, leading to an increase in boiling and melting point. Dispersion forces occur between all molecules, whether they are polar or nonpolar. Hydrogen bonding is an exception to the increase in molecular weight will increase the boiling point rule, and none of these intermolecular forces are as strong as ordinary ionic or covalent bonds, otherwise classified as intramolecular forces. So what did you learn? We talked about the difference between inter and intramolecular forces. We referred to ion dipole forces, dipole-dipole forces, London dispersion forces, hydrogen bonding, and looked at the impact of intermolecular forces on phase change. Need more help? Feel free to contact me. Have a great day.